In this tutorial, we will cover the basics of what graph is, how to build and verify a max graph using Mojo, how to compile a graph, finally, how to execute a graph with inputs. We will then use the max graph API to implement a two-layer feed-forward neural network with value activation for inference on MNIST data, and compare the accuracy to our PyTorch implementation. Lastly, we will learn how to create a custom operator using the MaxGraph Custom Operator API. First, let's define what a graph is. A graph is a mathematical object. It has a set of nodes and edges. Here is a simple example of a graph that has two inputs and one output. And in fact, this is a computation graph because we are adding input 0 to input 1. So it represents the addition computation. Here is how to use the MaxGraph Mojo API to define such a graph. We first import the necessary module. We then need to define input types. So here, these are just numbers, float 32. We can get the first input and second input by using the index. We do the addition and assign the outputs to the graph. We also verify the graph, which checks for various structural integrity, such as the graph shouldn't have any cycle. We also print the graph for visual inspection. To load and compile the graph, we create an inference session. We'll load the graph into the session object. And to execute the graph with some input, we create two inputs, tensors of 1, and use the execute method on the model to pass the inputs. And finally, here is how to get the results. Now let's compile and run the code. The first output is the textual representation of a graph. We also print the input names and the input values of the results. For the next example, we will create a matrix multiplication graph known as matmul. It has a single input and it's doing matrix multiplication of input 0 by a constant matrix, which is represented as a constant symbol here. This type of graph is particularly important as it demonstrates how constant symbol representing trained and fixed weight in a neural network can be utilized. Now, to define such a graph as before, we create the graph object because it's going to have a single input of tensor type. So the tensor type is going to be of type float 32, and its dimensions are going to be n by 2. N here is a symbolic dimension. To create a constant symbol, first we create a constant tensor of 2 by 2 with all the values be 42, and we use the graph.constant to create the constant symbol, and after that we perform the matrix multiplication. We assign the output to graph and verify it. Now, as before, to load and compile the graph, we create a session object, load the graph. Now, to execute the graph with some random inputs, here's how to create a random 2 by 2 matrix, pass it to the graph using the execute method on the compiled graph, and we get the result. One thing to note is that because we've used the symbolic dimension m here, we can also pass another matrix 3 by 2 to the compiled graph and execute it and get the results. Okay, let's compile and run the graph quickly. Here is our constant symbol, and here's the random input, random output that we get. Also 3 by 2 versus 2 by 2 result. We've covered the basics of MaxGraph API in Mojo. Now let's see it in action. We want to train a two-layer neural network on the MNIST dataset. MNIST dataset is a very famous dataset historically, and it's small enough, which is great for demos and tutorials. This dataset consists of handwritten digits 0 to 9. Let's look at the PyTorch code that we want to use to train a model. Here is a simple 2-layer neural net. Now let's go and train our model on MNIST. We are going to see the test results roll, which is 97.31% on test images. This is important to remember because we are going to recreate this model using the Graph API, and we're going to test it again for inference on these test images. And we should get exactly the same accuracy. Now let's see how to use MaxGraph Mojo API to implement our neural network. Here we define our graph with a single input, with a symbolic batch dimension, and 28 by 28, which is the size of each MNIST image. In PyTorch, linear layer is defined as the data multiplied by weight transpose plus the bias. First, we need to load it tensors into constant symbol and transpose them. We perform the matrix multiplication and add the bias. We'll talk about custom ops later. For now, we use the ops.value. And for the second layer, we do exactly the same thing as we did with the first layer and explicitly include softmax because we want to get the probabilities out. We assign the output to the graph verified. Here is how to load NIST test dataset in Mojo using Torch Vision. Also, this is how we pre-process each test image using Torch Vision transform. And after loading the weight from NumPy and converting them to Mojo tensor, we build the graph, we create the inference session, load the MNIST graph into a session object, which compiles our graph as well. And finally, we iterate to test image. We apply the pre-processing to each image. We execute the model with the pre-processed images and get the result out. We also use argmax to find the predicted labels. We also get the labels, the actual label, and compare if the prediction matches or not. And finally, we print out the accuracy of the network on our test images. Let's quickly run the code and see the result. Here we are printing the tensor shapes for visual inspection. And finally, if you remember, the PyTorch implementation, the test result was 97.31%, and here we are getting exactly that number. In the final section, we are going to see how to use Max custom operator API to implement a custom operator, which is useful for implementing new operators that doesn't exist in Max, or you want to optimize an existing operator, or to have your own implementation for any reason. For that, we are going to use Relu 6. Let's run the code, see the result. Okay, the accuracy we got is 95.91%. We're going to see next how to implement Relu 6. Custom operators in Max need to be in the format of Mojo package. Here is an example of a Mojo package that implements Relu 6. The package name is custom ops. It has inits, Mojo, and also Relu 6. The implementation is in the Relu 6. For that, we are importing register from Mac. Register is a decorator that is going to register a function as a custom op. Here we are giving a name, value 6, and the actual implementation is using the extensibility tensor. The function implementing the custom operator needs to have the following properties. It can only take tensors and can output a single tensor, cannot raise any expression. So with that in mind, in the init file, which makes this folder to a package, a Mojo package, we're going to import value 6. The next thing we need to do is to call Mojo package or the custom ops that will create custom ops.mojo package for us. Now we have our own implementation of value 6. If we go back to mnist.mojo, we need to make two changes. One is instead of using ops.value, here we are using ops.custom and giving it the name, the input tensor, and also it in type. The second thing that we need to change is when we are loading a mnist graph into the session object, we need to give the custom ops path, which is the custom ops.mojo package that we created. With those in place, I can now use Mojo to compile and run mnist using value 6. The initial output is the same, and we should expect to get the exact same accuracy, which is 95.91%. And that concludes this tutorial. Let's do a quick recap. We have covered the basics, defined what a graph is, show you how to build and verify a max graph in Mojo. We've seen several examples of how to load and compile a graph and how to execute a graph with inputs. Then we used our knowledge to implement a simple neural network in Max and compare its accuracy to PyTorch on mnist datasets. And finally, we implemented a custom value 6 operator using Max custom operator API. And we've seen how to package and compile it for execution. That finishes this tutorial. Thank you for watching. Until next time.